Sample rate is the frequency with which data is collected. Typically, sample rate is measured in hertz or samples per second. For example, a sample rate of 44 kilohertz will include 44,000 pieces of data per second. When collecting data by means of an analog to digital converter, the data will be stored and displayed as a series of voltages corresponding to the information being sampled. If one does not properly select a sample rate, the data collected may show trends that are incorrect. Take the following image for example. Both pieces of information are collected from the same source data but with different sampling rates. While the event being sampled remains the same, the points collected tell a different story. This is called aliasing and will be discussed later. In relation to audio recording, digital audio uses pulse code modulation to recreate audio, and these pulses are measured in hertz, as the amount of samples per second relate to how the audio will sound when replayed. When a piece of audio is recorded using a low sampling rate, the audio heard will be low quality. However, as the sampling rate increases, the quality of the audio will increase. See in the following audio clip the differences in quality simply due to the different sample rates. The upper and first played track has been resampled at a rate of 8,000 Hz, and the lower and second sample is at the industry standard of around 44 kHz. As the waves then zoom in, you can see the difference in sampling rates. At first it appears as more noise on the lower wave, but as you get even closer, you can see the individual data points, the difference in frequency being the direct reason for the differences in audio quality.
As we know, aliasing occurs when the sample rate is too low. However, the Nyquist theorem gives us a nice way to figure out whether or not aliasing will occur and how to combat aliasing. The Nyquist will give us the sample rate required to experience no aliasing. This occurs whenever the sample rate is twice the highest frequency that you will experience during your measurements. This will allow us to adequately represent the data with the sample points taken. From the Nyquist theorem, we can learn two things: the Nyquist rate and the Nyquist frequency. The Nyquist rate is the sample rate that is required to adequately represent the waveform according to the Nyquist theorem. And the Nyquist frequency is the highest frequency wave that we can adequately represent at a chosen sample rate. These two are very similar, but it is important to know the difference. An easy way to remember which is to remember that a Nyquist rate refers to a particular sample rate. They both use the same terminology: Nyquist rate, sample rate.
Aliasing in terms of data acquisition and sampling is the misidentification of a signal frequency, which as a result will introduce errors and an incorrect frequency. Aliasing will occur when the sample frequency is higher than double the signal frequency. In this Excel file, the signal frequency is shown to be 10 Hz. As sampling frequency increases, the accuracy to the real frequency is also increased. When the sampling rate is 10 Hz, it can be seen that it is just a horizontal line and will completely miss the frequency. At 11 Hz, it will look like it has a lower frequency than it actually does. At 21 Hz, it starts to include some of the peaks but doesn't look like the analog frequency entirely. At 50 Hz, it will begin to look similar in shape to the analog frequency, but it will have some rough edges. Normally, the sampling rate should be at least 10 times the signal frequency in order for it to be accurate. At 100 Hz, the comparison of the analog signal and the digital signal will begin to completely overlap. As the sampling rate increases more and more, as shown by the 1000 Hz sampling rate, then it will begin to almost perfectly overlap.
Resolution is the ability of the measurement system to detect and faithfully indicate small changes in a characteristic of a measurement result. In other words, it is the degree in which change can be theoretically detected. When looking at a digital device like a multimeter, the resolution will be the least significant digit.
Quantization is the process of converting data from a larger set to a smaller set. Typically, this occurs in analog to digital converters when they take continuous real-time data and turn it into a series of discrete values for given times. This allows a previously uncountable data source to be made into a countable and thus usable one. Quantization error is the difference between the measured data and the real data. In the pictures shown, the red line represents the analog signal, and the digital quantized version of data is represented by the blue line.
Data saturation occurs when all of the data that can be represented is currently being represented, and no new data trends will emerge with the collection of more data. Another way to put this is that if we continue to sample, no new concepts or linkages between the concepts will emerge. No additional data is needed, and no aspects of the theory or model remain hypothetical. Everything is confirmed at this point. True data saturation almost never occurs. However, we can almost always reach theoretical data saturation. This will occur at differing points for differing experiments, depending on what is required. Data saturation can be reached for both qualitative and quantitative data. We constantly experience theoretical data saturation in lab, whenever the data levels off and we stop the recording of data. We do this because we know if we continue to measure data, no new trends will emerge that have any significance.
Single-ended input is when you only have one signal line that is measured relative to the ground. As such, this is generally done to reduce the number of wires needed to measure the sensors. The downside of doing this is that the signal is very susceptible to EMI noise, which causes a larger signal compared to the resolution. Single-ended connections are only suitable when all the analog signal is made to be relative to a common ground point. This is because different ground points have different voltage values, which can distort the data. Differential-ended input does not measure the signal relative to the ground, but instead through two distinct input signals, so that the measurement voltage is the difference between the two input wires. By doing this, noise can be greatly reduced because the noise can be filtered through common mode rejection. You would use differential-ended input when environment is noisy or the sensors are prone to noise. The figure on the right shows the differential-ended input where two input signals are isolated from the ground.
Amplification is the range in which an instrument will collect data. Anything higher or lower than the maximum or minimum of the data will output the maximum or minimum amplification. If amplification is just slightly higher than the peaks of the signal, the resolution will be best. If amplification is too low, then it will begin to cut off the data of the peaks. Filters edit the raw data to where it will only show the desired data. Hardware filters will alter the data as it is being taken, and it cannot be removed. Software filters, however, can be used during or after taking the data and will not alter the raw data. As you can see in the graph in red, that is the raw data. When a low-pass filter is applied, it will keep the low frequencies and remove the high frequencies, which can be seen from the graph in blue. This is mostly used if there is a lot of noise in the data. When a high-pass filter is applied, it will keep the high frequencies and will remove the low frequencies, which can be seen from the graph in green. This is mostly used if the baseline is not constant and moves around a lot. The difference between an analog and a digital filter is that digital filters need to be converted with an analog to digital converter to change into binary numbers, which will then be processed with a microprocessor and converted back to an analog signal using a digital to analog converter. Analog converters, however, will use an analog signal the entire time it is being filtered. The good things with digital filters are that they can filter very low frequencies, are easily standardized, and most things already come with a microprocessor. The good things with analog filters are that they do not need an algorithm to work, unlike the digital converters, or digital filters, and they do not need a microprocessor, and it also uses fewer components.
An offset null circuit can take a voltage input and offset the output by the corresponding amount. This type of circuit generally uses an op-amp. Typically, offset null circuits will use a potentiometer to vary the voltage input to the offset null portion of the op-amp. Offset null circuits are generally used to offset data or to bring it back to zero. The offset can be whatever is required at the time and can offset the data wherever needed. It can be used to zero and calibrate devices by bringing the current value to zero. These are very useful and used in most measurement software in order to calibrate back to zero. We can see here that the accelerometer consistently measures a 9.81 acceleration in the negative direction. This is due to gravity. If we were wanting to measure relative acceleration instead of absolute acceleration, we could use an offset null circuit in order to bring this data back to zero. Here we can see that an op-amp has an offset null input. This is where you would apply the voltage you want to offset the circuit by.
Resolution, range, and sample rate are important because resolution allows for a complete look at the data being examined. As can be seen from the picture, with lower resolution, the data collected could not completely acquire all the data points for the sine wave. It only goes to the limit in which the resolution is set. From that, knowing the range of the measurement in which the maximum and the minimum value are to be set can help define the resolution. That is when range are very important for the experimental data. Sample rate is how much data is collected per increment of time measured. High sample rate allows for a complete data collection. As can be seen from the picture, with low sample rate, the data collected were few and far between. This creates a completely different graph even though the data points collected are part of the actual graph. Higher sample rate allows for more data sample per unit of time measured. You can hear it from the early example of sample rate.